Okay, let's start this video regarding how you calculate the parameters of the synchronous machine, the direct axis reactance and transient and subtransient reactances, as well as the transient and subtransient time constants. Okay, basically what we have, sub transient and transient parameters of synchronous generator. Okay, E, 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 and G, 311. Okay. Basically, we have a generator, three-phase generator. Okay. And we make a short circuit. Then we get IA, IB, and IC. Okay. If we start this using a circuit breaker, okay, if we have a circuit breaker, we close at time the 3 poles at time equals 0, then we will get the current. Okay, let me just define three values here. Okay. Basically what we will get is sinusoidal wave like this. Okay. And it will continue like this. Okay. It will continue exponential like this. This is what we have, IA. Now if we go to the maximum values of this here, this is a point here, here is a point here, another point here, another point here, another point, and it will intersect the exact the y-axis and this point. So let's name this as IA equal current envelope. Okay, experimentally you indicate these points, okay, at the maximum, and this is time. Okay, so if we look to the envelope again, that you will do it experimentally. You will make a short circuit, you close this one, you make a short circuit, you plot the current IA, you will get something like this, and on a paper you indicate these maximum values, okay, and you store them in the computer. You store each time with each value, okay. Then what you will get really is something like this. And this is IA. This is IA. So, and this point here is IA 0. So you get these points. Okay. So these points represents the envelope of the armature current, time and I. Okay, so this is IA. Now we can assume that the current has three components. First, IA equal I steady state plus I1 E minus 1 O tau d transient times t plus A2 e to the minus 1 over tau subtransient time constant t, this times sine omega t, where omega equal to pi f equal 50 hertz or 60 hertz. Okay, now the this represents the envelope. This is the envelope. Okay, so IA, okay, let's say this is IA, let's give it a name, IAX. So IA envelope is equal I steady state plus A1 e to the minus 1 over tau transient times t, okay, plus A2 e to the minus 1 over tau t subtransient times t. So this is the envelope. Okay, so it has basically three components: the steady state component, the transient component, and the subtransient component. Okay, at time equal 0, we have IA0 is equal I steady state plus A1 plus A2. Okay, at time approaches infinity, IA naught is equal IA infinity is equal I steady state. Now this is known, and this is known. Both are known. If you look at the curve, we know this I steady state is here and I naught is here. Okay? Now we don't know A1, we don't know A2. Okay? And A1 plus A2 is equal I A naught minus I steady state. Let's say this is equal K naught. So we know it, no. But we don't know A1 and A2 equal what? We don't know. We have to determine. As well as the transient and subtransient times constant. Okay, we have to determine that. Now, if we look again to IA, this is IA, and this is I steady state. So this one here is A1 plus A2. Okay? Let's call it Y. This is I A minus I steady state, okay, which is equal Y. Okay, we go back to it. Okay, here is K naught, okay, which is equal Here A1 plus A2 equal K naught, okay, on this point, and this is time. Now, how to separate A1 and A2? Now, this, if we, y IA minus I steady state actually is A1 e to the minus 1 over tau transient times t plus A2 e to the minus 1 over tau subtransient times t. Now we don't know time constants and we don't know A1 and A2, okay, but at time 0 this will be 1, this will be 1, so A1 plus A2 at time 0, which is K naught, okay? Now, if we take the log of y, when we say log, natural log, which is equal to ln, okay? Then ln y, okay, will be is equal ln A1 e to the minus 1 over tau d transient t plus A2 ln A2 e to the minus 1 tau d subtransient t, okay? Now, and this will be more or less non-linear. This is non-linear. This will be more linear paths for the two parts for the transient and subtransients. Let's compare them. We have this y. We'll be having, okay, so we'll be having something like this, okay? This is why this is ln y, okay? So here ln y, and here is y. Ln y, or we can call it let ln y is equal y on logarithmic scale, okay? So we call it ln y, okay? Let's say this, for example, to separate that. Let's y, this is y, let's say this is, for example, y bar, okay? Then if we take the log of y bar here, natural log, and log y bar, and let's name it y, okay? This is y. So we know this is y bar here, okay? And this is ln y bar, let's call this y. Now this, we can from this trace the two linear parts, okay? We can sketch this one, interpolate it until it intersects the point here, okay? So we know this point, okay? Now, how we calculate how we separate these two parts, okay? If we take y bar or y in a logarithmic scale, okay? If we take this transient y transient, okay, will equal originally it was e1 e to the minus 1 over tau d transient times t. But we have taken the natural log of that, and this is ln this, okay? Now, this is y, y1, let's name it y1 for example, okay? y1, okay, let's call it y1, okay. Now, this is equal ln a1 plus ln e to the minus 1 over tau d times t. So this is equal ln a1 minus 1 over tau d transit times t, okay? Times ln e, and this is 1, okay? So this is equal basically ln a1 minus 1 over tau d times t. So this point here is ln a1, okay? Let's say this point is, let's name it n1 for example, n1, okay? n1, okay? n1 equal ln a1, therefore a1 is equal exponential of n1, okay? So we calculate this. We know no a1, okay, from this. Once we know this point, we take the exponential of it, we get a1, because it is ln a1. Now, from that, the same curve, okay, y1, what is the value of y1 at time equal tau d transient? It would be y1 is equal ln a1 minus 1 over tau d transients times tau d transients, okay, which is equal ln a1 minus 1. So if we take this one here, the same here, okay, that curve, okay, if we take this, ln a1, okay. If we subtract this one from it, you wouldn't end up, let's say, this is ln a1 minus 1, this one. Here it will intersect the curve y1, now let's call this is y1, okay, y1, will intersect it at tau d transient. So we can calculate time d transient. So y1 at tau d transient, okay, is equal to a1 minus 1, okay? So actually we have two ways. We take y1, this is y1. If we take the original y, okay, original y, this would be something like here, okay. here is A1, and here it is A2, and here is, okay, it's just, here is A1, and here is A2, and here this point here, this K naught, called A1 plus A2, okay? That's the original point. So, this, originally, in actual y, but in log y, similar to this. This will be linear. This is y1, okay? And here is len a1, okay? This one is len a1, and this one is len a2, okay? So this is y1. So, to calculate tau d transient, we need here what? Len a1 minus 1. Or, in here, in this one here, this is a1, so this is a1 e to the minus 1. Okay? Either we use this method to calculate dye transients, okay, from y1. This is a1, multiply a1 by e to the minus 1. It will be this value here. It will intersect the curve at a point on the x-axis, which is equal to the time, the transient time constant, okay? Or you can use the len y, which is y1, okay? Then we can determine len y, okay? Just this loop, this one here, y1, okay? The linear part of the curve, okay? To calculate. In that case, you have it as, okay? If we go back to our example in MATLAB, I'll show you. In MATLAB, we have it, okay. I will not switch MATLAB, but in our example, let's go to the MATLAB notes. If you go back to your notes, and you check the synchronous of your project, in our example, okay, in our example, we have I steady state equal 1. We have I A naught is equal I steady state plus A1 plus A2 equal 5. Okay, so A1 plus A2 equal K naught equal 5 minus 1 equal 4. Okay, but we don't notice A1 and what is A2. And we obtained len A1 equal in the example. Len A1, if you check the example, okay, we obtained len A1 is 0.4055. From this, we obtain A1 equal e to the 0.4055, which is equal, I think, 1.5. Okay? So we obtained that experimentally, okay? That's A1, okay? Now, if we take on the same curve there, what is the value ln A1 minus 1 will be 0.4055 minus 1, okay? It will be 0.5945. It will be negative minus, okay? And from that, if you sketch it on the curve, this will lead to transients equal 0.4 seconds, okay? You can do it this way, or you can do it or on the Y curve, or on the Y curve, what is A1 e to the minus 1, which will give you time d transient equal 0.4 second. Okay, you can do it both ways. On the Y curve, on the log Y, ln Y, you use this curve, and the Y curve, you use this one. A1 at this point here, A1 e to the minus 1, or on the logarithmic scale, use ln A1 minus 1. Okay, either use this on the actual Y, or ln A1 minus 1 on the logarithmic scale. Okay, then this will determine A1 and time constant, transient time constant. Now if we take Y2 equal Y minus Y1, we go back to it, okay? Then, okay, this is Y. Let's say 2 and Y1, okay, and this is Y, and this is Y1, now we want to separate it. We said this is A1 and this is A2. Now we subtract Y minus Y1 and call it Y2. What you will get, this is Y2 equal Y minus Y1, okay? Y2 is equal to Y minus 1 minus Y1. You will get this one here is A2, okay? Now, for this Y2, we can use both scales, okay? Here is A2, and here is A2 e to the minus 1. You will obtain here time d subtransit using Y2, okay, or using the linear part, ln Y2, okay, you'll get here ln A2, and similarly at this point here, this will be ln A2 minus 1. Okay, you can use both. This one from len A2 and subtract -1 from it. Okay, or use A2 and multiply it by A2 to the -1. So this one here will give you len A2 from which you can A2 and len A2 -1 from which, or A2 e to the -1 from which give time the subtransits. Okay, in our example, in our example, okay, then A2 becomes 0.9163, okay, and then A2, you can calculate A2, okay. A2, okay, okay, A2 and A2, A2, A2 is equal e to the 0.9163, which is, I think, is 2.5. Okay, let me check in the MATLAB the answer. What is log 0.9163? 0.916. Exponential, sorry, exponential, yes, 2.5, okay, and at A2 e to the -1 on Y2 will give you tau d subtransit, which is 0.02 seconds. Okay, you can look at the example. Okay, you'll find it over the 0.02, or len A2 -1 will give you 0.9163 -1, which this will give you, okay, tau d subtransit equal 0.02 or so seconds, okay, on the len Y2 on the curve. Okay, so either use the logarithm scale curve, but to determine A2 it's important we use the logarithmic scale because it is linear. Okay, this basically how we calculate the constant, the parameters. Now we know I steady state A1, A2, tau d transient, and tau d subtransient. Okay? Now, steady state current I steady state, okay, ID is equal I steady state. We know it, okay? We know this. Now I transient, we add I steady state plus A1, okay? ID subtransient is equal I steady state plus A1 plus A2, okay? So we know these ones. Basically, if we look at it, this is ID, steady state. We add to that I1, this is ID transient, and if we add A2, ID subtransient, okay? This basically is the current I, envelope, okay? So here is I steady state, here plus, or this one is A1, and here is A2. So if we add to the steady state the part of A1, you will get the transient current, and the initial current is the subtransient current. Now, assuming, let this represents E maximum of the generator, okay, and equal constant. Then XD is E maximum divided by ID. So it is E maximum divided by steady state, okay? Now, XD transient is E maximum divided by ID transient. So it is E maximum divided by I steady state plus A1. And XD subtransient is equal E maximum divided by ID subtransient. So it is E max divided by I steady state plus A1 plus A2, okay? So in our example, E maximum equal 1, I steady state equal 1, A1 equal 0.15, 1.5, and A2 equal 2.5, okay? So XD equal 1 over 1, this is 1 per unit. XD transients equal 1 over 1 plus 1.5, that's A1, which is 1 over 2.5 per unit, okay? And XD transients is 1 over 1 plus 1.5 plus 2.5, which is 1 over 5, okay? Per unit, okay? You can calculate that. The most important, when you do an experiment, remember that if E is in per unit, and I is in per unit, okay, then Emax equal root 2 ERMS, okay? So if ERMS is 1 per unit, then you multiply by root 2. Because why? Because you are taking the envelope, the maximum. This is E maximum, okay? So in that case, E maximum is root 2. This is just a scaling factor, okay? It's very important you understand that. So it's basically this regarding understand it and do the project. When you do the project, in the project, what you have, let me check the project again. What you have in the project, you have, for the project, you have up to 4, you have something like this, okay? That's what you have, right, in the project. You have up to 4 seconds here. And the maximum, you try to find approximately maybe 2.5 here, okay? So you put a tracing paper on the here, on this one, and try to determine several points here. You don't need to go to many points, but sort of enough points. In the project, try to find out, for example, 4 seconds, you may scale that to say 20 or 50 points. Try, for example, 40 to 50 points. Okay? For example, here what is IA? Okay? Take T and IA, this is IA, okay, and IA for 40 to 50 points to get better approximation, okay? So it means 0, for example, T1, T2, up to 4 seconds, okay? This is the T. In steps, say, if you take 0.1, T equal 0.1, that will give you to 1 second, that will go to 40, for example. If you take 0.1, for example, then 0.2, then 0.3, and so on, okay? And similarly, IA naught, IA1, IA2, and so on, to IA at 4 seconds, okay? A at 40, for example. So if you take this, for example, time, this is IA1, TA1, calculate this IA1, okay? TA2, IA2, TA2, and so on, okay? Take enough points, 40 to 50, okay? The more points you take, the more will be the accurate calculation, okay? And you have 2 scales there, up to 1 or so. You can choose, for example, the 1, or take the scale of 1, what you have, the 1, right? This is what? Oh, sorry, this is not y, it's IA. Or you take the IA to 1. You have it also, I can see it in the, on the project, okay? Maybe utilize this better. But still, take 40 points, for example, from point 10.025, for example, okay? Take t equal 0 to 1, and for example, 0.25 steps, okay? 0.025 steps, right? Or 0.02 and say 0.02 steps. So you'll take in that case maybe 50 points. So t will be 0, 0.02, 0.04, 0.06, 0.08, 0.1, and so on, okay? Similarly, find what is IA, which belongs to this. This one will be maybe 2.5, and so on. 12 values, okay? How you do it? Just put a tracing paper here, on this one here, and indicate these points. It's not necessarily that you go exactly to 0.02, okay? Just indicate this point here, and see what is T1, what is IA1, what is T2, what is IA2. Here is T2, I2, here is T1, I1, here is 0T and IA0. At any point here, calculate what is Tn, what is IA at time n, okay? You have enough points, let's say 50, okay? And then from these papers, you just follow the how you can translate it to logarithmic scale, and how to determine A1 and A2, the time constant one, the transit time constant, and subtransient time constants, okay? This basically regarding the project. What I did also, I designed a small program. We can also utilize curve fitting. Those students who takes numerical analysis ENG 205 with me, they can utilize, they know how we do the curve fitting. For we can utilize curve fitting using, for example, using Newton, Raphson method, okay? How we do that is very easy. We know IA envelope is equal I steady state plus A1 e to the minus 1 over time transit T plus A2 e to the minus 1 subtransit T. Okay, let's just simplify it as I steady state plus A1 e to the minus, let's say H1 T plus A2 e to the minus H2 T. So find A1, A2, H1, h2 I steady state. Okay. Now we know I steady state. Okay. We know also IA naught. So IA naught should equal I steady state plus A1 plus A. Okay. Then IA naught minus I steady state equal K naught equal A1. So we know the sum of A1 and A2, but we don't know which one, what is the value of A1, what is the value of A2. So we know Y is equal IA minus I steady state. So we know Y equal A1 e to the minus H1t plus A2 e to the minus H2t, where tau transients equal 1 over H1 and tau subtransients equal 1 over H2. Okay? So basically we have 4. Okay? But we know K naught equal A1 plus A2. So we can simplify it. Y is equal A1. Let's call this is a function. Y equal function A1 e to the minus H1t plus A2 e to the minus H2t, and this is equal E1 e to the minus H1 t plus, this will be K naught minus A1 e to the minus H2 t. So what we need is A1, H1, H2. So we reduce the parameters we have to calculate to 3, H1, H2, and A1. Once we know A1, we can calculate A2 from this relationship. Okay. How to do that? Assume function equal A1 e to the minus H1 t plus K naught minus A1 e to the minus H2t. Okay? This suppose the function. This supposed must equal Y, which is equal IA minus I steady state. Okay? It won't be exactly the same, but we try to find the parameters that best fit Y. So we use least square fitting, the minimum of that. Least squares, we take Y, this one, minus the function, we square it, we can also multiply it by half and take the sum for all points. This calls index. We want to minimize this. Okay, minimize, let's say it's J, minimize J. What is the index J? The minimum least square. To do that, we take J equals sum of Y minus F squared half. We take the derivative of J to A1, let's call it F1, derivative of J to H1, let's call it F2, and derivative of J with H2, let's call it F3. So this must go to 0, okay? The derivative optimization, when to optimize, minimize the least square or optimize the problem, we want to find what is A1, what is H1, what is H2, that best minimize this index, okay? Then we calculate the Jacobian, what is df1 with dA1, okay? What is df1 with dH1, what is df1 with H2, and also what is df2 with dA1, what is df2 with dH1, what is df2 with dH2, and we have what is df3 with dA1, what is df3 with dH1, what is df3 with H2. This is known as the Jacobian, equal Jacobian, okay? This is Jacobian matrix, okay? Based on this, so we know it, we can calculate, let's say, delta equal Jacobian inverse times F, which is F1, F2, and F, okay? And we update A1, H1, H2 at iteration, let's say K plus 1, here iteration is equal the previous one, A1, H1, H2 at iteration K minus Jac inverse times F1, F2, okay? We updated this one, okay? Most important that here is K evaluated at K, this Jac evaluated at K. Most important is that we start A1, H1, H2 at a reasonable value. Start A1, H1, and H2 at reasonable values, okay? A1 approximately equal K naught over 2 is reasonable, okay? Also, tau d transient is greater than tau d subtransient, so it means H1 is less than H2, because H1 is 1 over that, okay? You can start these values and, okay, so I have designed just a program, named it sync, I think parameter. I will just upload it to you. You can try it and compare also. Your method in the project, use the method, the parameters you got from the project, you can use them as a start point for this, and you practice it also. And for those who takes 205 with me, also you can try it. If you want it, I can upload it. I will upload this program in EENG 311 through the Blackboard, as well as through the WhatsApp group, okay? And I will close now this, okay, this video, I don't know if you need another video just using the MATLAB show you how you manage to do the program probably, but you may not need that. I will try to. I can make it just for 5 minutes. Okay, just use the camera and show you the MATLAB program. Okay, but I will upload it to you. Okay, so maybe next week I will start another test with you. So just be prepared, okay? Read, for example, we have taken a test on line parameters. Now, I want to probably to make a test, a general test on the representation of lines, ABCD parameters or such as well, okay? ABCD parameters, and I will choose the topics, okay, and write and tell you about that. But it's not in my mind now exactly what topics are. But okay, but be always prepared. Now you make this a project, continue it, and send it to me through the Blackboard. Okay. Talk to you later.